Okay, thank you for coming. This is going to be an update on the presentation I made last year after the discovery, the first discovery of gravitational waves. So let's see what is going on Virgo, trying to catching on the astronomy of gravitational wave. So this is the outline. We will have just a bit of a recap on what detecting gravitational waves with interferometers. Then we will see the global detector network. We look at what's going on with advanced Virgo and specifically with the commissioning of advanced Virgo. And then we have a look to what Python means for controlling the machine and its commission. So what we have to do for detecting gravitational waves with the interferometer, just a reminder of what. So just a reminder what means trying to detect gravitational waves. So we are trying to look at gravitational waves, so space that is squeezed and stretched, and what at the end of the story we are looking at is a relative variation of distance, delta L over L. So we need a set of free test masses very far apart, and and a way to measure their relative distance, and also motion, relative motion. And we need to have those like free-falling masses. That's the idea. So we want to have free-falling masses that are completely isolated from any other cause of motion. So even the most tremendous event in the universe, the one basically that we detected, can this strain. This is the order of magnitude what we are looking for, 10 to the minus 21. It means at the end of the story that you want to be able to look at a change in terms of length at the 10 to the minus 18. This is if you want to compare, we would like to look at the variation of the distance between here and the sun. The variation we are looking for is of the size of a proton. So that's what we're trying to do. Now, to detect the gravitational wave, we are trying, so after some experience with different kind of detector like resonant bars, scientists ended up that the most effective way to try to do this measurement was using interferometer, laser interferometer. So laser is used to measure the relative length of those arms. The idea is that if there is a gravitational wave passing through, the change in length on the two arms will be different, and then you can detect it on the change on a photodiode here on this side. So basically you have the laser beam going up and down. This is making your measurement, and then you keep the waves inside in destructive position, and then here basically you have what we call the dark fringe, and if you see something on the photodiode, it should correspond to a signal that gravitational wave has passed. So as I said before, in this case, we make the arm length at least a few kilometers. If you make the arms a few kilometers, that's allowed to go in the order of magnitude I was mentioning before. So you could try to make this measurement. So we made a first generation gravitational wave detector. The nominal sensitivity was set more than a decade ago. We reached that sensitivity, but no detection were made. I would like to just to point, I mean, apart these graphs, what is really important are the dates. So what I would like to really stress the fact, it took us from 2003 to even 2011 at the end of the story to reach the sensitivity we were targeting. So this is the time it takes you to make this machine running. And I would like just to you keep in mind those dates and you compare with what we are trying to do now. We are trying to make a second generation machine running, and we are trying to squeeze this, say, 7, 8, 9, 10 years of commissioning at the end of the story in few months. That's what we are trying to do. Let's see if we can succeed. So now, since we didn't see anything, the scientists came up with the idea, okay, let's make machine 10 times better. And it was already a nightmare making the first generation machine. And when they said this to us, I said, yeah, good. I mean, it was already so difficult making the previous one. And then you want 10 times better. Okay, let's try to do it. So they asked for a 10 times improvement for the sensitivity. But what is really important is like a 10 times sensitivity improvement means 100 times increase on the volume of the universe that you can observe, and within this volume there is something that is powerful enough to be observed, you can see it. This is what implies that just a single day of advanced detector data acquisition is the equivalent of 1 year. So this is why we are pushing, and we are if you look at it from the outside, it seems, but why you are not staying there and collecting data? But the fact is that if you are able to make your sensitivity improve, then again, 1 day of science can pay you 1 year. That's the basic point. So this is why you are keep pushing and pushing to make it better, because the gain you make it's at cubic, okay? So you are always trying to do it. So a bit of history is that what is really important here is the fact LIGO has at least 2 years of advantage in terms of time. And because the approval of advanced LIGO was at least 2 years before, and what we did in reality, Virgo remained online at this time to compensate, to have at least for as much as possible on one detector available while LIGO was upgraded. So they have 2 years advantage, but also look at those numbers in terms of money. So advanced LIGO was founded with $205 million. We got founded with 21 million euros. So this is the comparison. Okay, on the other side you have 2 detectors. Then you can say, okay, these numbers are also a bit different because inside here you don't have the salary of the people working inside. But even put 10 million more here. Then at the end of the story we are comparing, okay, single detector is almost a factor 3, factor 4. So we are trying to do exactly what the Americans are doing with 4 times less money. And this, I tell you, is an heroic attempt. Just comparing it. So, but the thing is, the gravitational wave astronomy has started and is definitely awaiting for us. So last year, I was talking about the September 14, 2015 event with 2 black holes collapsing. We have now another event confirmed in December 2015, and also we have another candidate already. So you see, astronomy has started. The first event was confirmed with another one. Candidate events are coming, and more things are coming with the second science run that is going on at the moment. So things are going on, and we have to catch up. But why? Why is also important to have advanced Virgo in the loop? Because laser interferometer are not like telescope. You cannot point on the sky. So sky location can be only reconstructed through the time of arrival of gravitational waves. And for the first event we have seen, the sky location is like this one, so very, very, very uncertain. So instead, if you keep adding other detectors, like in this case you have the 2 Hanford and Livingston advanced Virgo detector. If you add that advanced LIGO, if you have also Virgo in the loop, I mean you see the capability of pointing into sky become even better and better. So this is what we are expecting, also considering that other detector will come into the network. So you see, if advanced Virgo would have been there during this event, the pointing in sky would have been better than 20 square degree. That is quite relatively good for our detectors. So we have advanced Virgo here, just in Kashmir, a few kilometers from where we are. We have the two advanced LIGO detector in the two corners of the United States, so they made it on purpose. They try to put them as far as possible because this way the signal you collect are better. Then there is also a detector in Germany. But since it's only 600 meter length, it doesn't have the capability to arrive to the sensitivity we need. But it's been mostly used as a test bed. It's working, and it's working quite well, and it's been a test bed for many technologies. Coming online soon, very soon, is going to be Kagra, that is in Japan. Kagra can be considered a 2.5 generation interferometer. It's putting also into it some different technology. It's an underground detector. It's been built in a dismissed mine, and is also trying to use cryogenic technology. So this is really also for them that the challenge is very strong. And also online, most probably now that has been approved, there will be the so-called Indigo, that is the India LIGO. Basically, the LIGO is kind of providing hardware, or big part of the hardware they have available to India, and India is providing all the facility and site support for building a detector there. And probably in 2020, okay, in the next decade, they should also be online. What is also important is the fact once you can really point in sky, then this enable multi-message astronomy, because at this point you can ask somebody else to confirm the event you have seen. So you can do two ways. So you can, what we call the lookup strategy. So if we say, okay, we have seen something, we can point in sky. At this point you can ask a telescope or satellite to point in that direction and confirm that they also see something. For example, if you see a signal that corresponds to a supernova that explodes, you can ask the other detector to confirm that they see something at that location in sky. And it's also the contrary. If satellite or other experiment, like for example neutrino detector, if they see something, they can tell us, please try to confirm the fact that in this position in sky you see something, or at least that you have seen an event that could match what we have seen. And also this definitely, also because at the moment we have very poor pointing in sky with the two advanced LIGO detector, we need a third one. So a bit of recap for what concerns Advanced Virgo. Advanced Virgo is a project in which all those laboratories in Europe are participating. The two, let's say, funding countries are Italy and France, and also Holland, Hungary, Poland, and Spain are coming in. And yeah, we are part of the international network together with LIGO. So we have an MOU, a memorandum of understanding, and this is why also in this case the data analysis is completely common. Virgo and LIGO groups are working completely together on the data. We are sharing completely the data. So the idea is that once we will be online, the data will be analyzed all together. So the two LIGO detector and the Virgo detector, we create a 3 detector machine in which all data are analyzed in real time. So what we call pseudo online analysis, just quick analysis to understand if you have seen something interesting, and the offline analysis where you are just crunching data all the time. Now, what is the difference? What are the main difference respect to the previous first generation detector? We have larger beams that are passing in the optical cavity. We have heavier mirrors. We try to push a lot on the technology for optical quality. So these optics are really extremes Basically, there are only 1 or 2 companies in the world that can build what we need, and there is also a specific laboratory built in Lyon, in France, that is doing the coating of our mirrors. And this is just unique because we have absolutely unique specification for the optics we need to use. We are introducing much more, let's say, complex thermal control of aberration. So the idea is that when a laser beam is passing through those optics, the beam hit the optics and distort the optics. So you need a way of reconstructing the shape you want of your optics because it's been distorted by the heating. We needed to have a much more strong, what we call straight light control. So you don't want any photon going around. You see, you cannot afford to have light that is hitting somewhere, so some beams that are going around, because all of them will become disturbance on your measurement. So you want all your photon doing exactly what you need, and especially in staying in this straight path between the mirrors. And also we increased the quality of the vacuum. We are talking about that all this stuff stays inside vacuum containers. The vacuum we are able to reach there was 10 to the minus 7 millibar, and we were able to go down to 10 to the minus 9. So what is the progress at the moment? Big progress has been made. We mounted the last mirror, so the last test mass, as I was mentioning before, in July 2016. In November, the ITF was completely available for commissioning. We made the first lock at half fringe. So basically, as I explained before, so you are locking all your optical cavities, and then you want to go in dark fringe. So in this case, half fringe means that this is half dark, as you want. And in February, just this year, we have been able to do the lock dark fringe. So the machine was brought to its working point. And we have been able to do it just for 15 minutes, and now in the last weeks, we have been able to make it this stable. So we are able to stably go to this working point, and this is very important. At this point, when you are there, you can really start to hunt for noise, to really understand what is wrong in the setup of the machine. So for us, it was definitely time for celebration. So this was really a major achievement. Now, what is the path to? So our goal is clear. We want to join LIGO on the second observation run that is going on at the moment. They are waiting for us, and they are always keep asking where we are, how we are doing, and when we can join. And so what we need to do is prove the stability when we are at dark fringe, but as I said, this is something we almost already achieved, so this is basically done. We need to improve the alignment loop. So the idea is that once your mirror are locked, so the laser beam is bouncing up and down in your optical cavity, then you have to be able to keep it there. So you have to have a very stringent alignment control so that the mirrors stay where they are. So the idea is the following: you really want your masses to be free falling, but the interferometer, once it's locked, is like is free falling itself. So it doesn't really matter. All the optics do not have to stay still. What is important is that they must stay relatively still. So the idea is that once everything is locked, your interferometer is moving in space, as long as this distance remains the same. But this is what is happening. We make it free floating, the whole interferometer. That's the idea. And then what is important that you keep the alignment, but the absolute position of the mirror change, and they do change. There is a small drift keeping going around, but what is important is that your masses stay in relative distance, all absolutely the same. So so there is a last part of the detector, this so-called, I show you here. So you see, at the end, You have this output mode cleaner. This is kind of a filter for the laser beam. We need to put it make it working. And again, this is happening just right now. We have to go to what we call low noise actuation. So at the moment we are controlling the mirror, but in a noisy way. We need to scale down, order of magnitude in the noise we are injecting while controlling the mirrors. We need to build this, what we call the noise budget, and also sensitivity curve. And for this, I have just what we can say freshly baked sensitivity curve. This is the main things we need to create, and we have just a few days ago come out with the first sensitivity curve of the machine. Then we will do weekend engineering runs, so we will try to run as in science mode. So we will leave the machine running for the weekend. We will collect data just to understand which are the performances. And with more commissioning and nose hunting, we may be ready to join LIGO. So now let's have a look more in detail what's going on for what concerns the use of Python. You see, we have a system that we need to control. We do it with two basic, say, different control loop. One real time. And this real-time loop is running at 10 kilohertz, more or less. This is the sampling rate we are using. And then we have a supervisory control or slow control loop. And this is exactly the place where Python can make a role. So, yeah, this is the Python application area, mostly for the supervisory control and also for the user interface for the operator in control room. So we had to spend a little time to understand how to link this supervisory control level made in Python with our fast control system. The problem was a bit complicated by the fact that we are still using, let's say, a legacy communication, inter-process communication system called CM. And at the same time, we are trying to bring in a new, say, control software framework called Tango. So we have to deal with two different systems. So by just exploiting the already existing library PyTango and creating via C-type gen bindings on top of the, let's say, C++ library associated to this inter-process communication layer, we have been able to create a library on top of those, and then your, let's say, supervisory layer is on top of this. So basically for us, these two systems become transparent. So you are controlling them in a transparent way because Python, so this Python library provides you all the abstraction level that you need. So then, to implement this control layer, we look at what LIGO was doing. LIGO was using the so-called Guardian, and Guardian provide a complete framework for the automation of your machine. And that was, okay, supervisory control or automation layer, based on hierarchical state machine. This system is fully developed in Python, and also the code you develop for controlling your system is made in Python. So what we have done, we went from Guardian to Metatron. And why Metatron? Because if you ask the question, who is the guardian of Virgo, the reply you get is the one of the angel of the guardian angel of the Virgo zodiac. So Metatron is, let's say, the boss of is the archangel for the Virgo zodiac. So it also was a nice name, and we adopted it. So we have performed the integration of Guardian in Virgo. We call it Metatron, and we are fully reusing whatever was available before there were already some script scattered around to do this kind of for dealing with the need of supervisory control. We collected all together, and also everything is based on the library I mentioned before, these Python Virgo tools. Also, we are using config parser for dealing with with the configuration parameter. And again, this is a very good example of Python as battery included. So you get Python, you need configuration, you need to deal with the configuration parameter, then you have a library and you just use it and you don't even think about it. You just, it's there, you take it, very easy to use. So this is again a good example of why Python is a good solution. Python is a good solution because you take it and many problems you may have just ancillary around, they are already most probably solved by libraries that are available. So one of the most important points to be dealt with was the integration with our data acquisition system. So we needed a way of integrating Guardian or Metatron inside our data acquisition system. And this was done by again, a specific development associated. And so basically what we are doing is that we are getting data directly from the shared memory, which does what we call frame builder for data acquisition. So we are able to get data and write data to our, so we embedded basically Metatron inside our data acquisition. So the idea is that Metatron is made by, again, as I said, those state machine. Inside those state machine, you have a main and a run that is run cyclically. In this case, our run is synchronized on the rhythm of the creation of the generation of our data, what we call frames, embedded inside frames. So, and inside this run, we made available a function that allow you to get channels to read data or write data. So this was one of the main developments that needed to be done. So this is the architecture of Metatron. Each node is composed by two processes, one daemon and one worker, that is really doing the job. And this is what is inside this worker. There is the user code, so the code that is developed by the scientist that needs to control the system. And also here you can see again the connection to the data acquisition. As I said, via the library we had developed before, we can connect to the system to be controlled either via CM or via Tango. Then you have dedicated interfaces in the control machine that you can use to drive those state machine. So this is the workflow. Basically, inside a web system, you have all the process. So to each state machine node correspond to a server that you can start and stop from here. Then you can launch this interface. From the interface itself, you can click and say, start editing your Python code for the job you need to do. You can also check what is the state machine you end up with. So, and then you can also change the code. One of the very nice things is that you can change the code and then dynamically load it. You can just push and load the code. This will automatically, so without stopping the control system, this is what is important. You want to keep running everything. You change your Python code, then you load it. This is very nice. So, and then the system just freeze, reload the code, and then you can just go on. So basically what is happening is that whatever state you are in, you stay in that state, you load again, you load your new code, and then you keep running. This is what is very, very, very convenient from the system. So you see, as I said, this is a hierarchical state machine system. This is a hierarchy at the moment. So basically, you control the single tower, then you control the arm, then you control, let's say, the different degree of freedom associated to controlling your interferometer. We have all documentation Python, let's say, Python compliant, and available on a website using Sphinx. And what is the current development? We stay always there in trying to support the ITF locking progress. For example, we support the calibration of the interferometer, the generation of, so you want to know in which state is your interferometer, if you are, for example, in science mode or whatever. And then also we need to deal with the noise budget generation. So this is one example of one state machine, and is the main one, so the one that deals with the locking the interferometer. You see, you have really a lot of steps that you have to follow to reach the final state of your machine. And if I have some little time, just very quickly, I would like to... control room. So this is the LIGO, the Virgo control room. And you see, there are in those two main screens, you see the mirrors at the end, at the west end and north end. So now you see, you look at those balls, that correspond to the state machine I was talking about. We have also a graphical representation with the states changing so people can know what's going on at the moment. So you see, look at what is going on there. So you see now, you see a little light in the mirrors. Now the two arms are locked. So basically the two optical cavity, the north and the west one, are locked. Now we lock in what's so-called recombined, and there we stay some time. Plus we engage a certain control loop called the second stage of frequency stabilization. Maybe we skip a bit and we look at the farther down. What is going to happen farther down? Look at what is going on in all those displays, and especially the one for North End and West End. The idea is that now we are moving the so-called power recycling mirror to create a recycling cavity for the power recycling. This increases the power. You see, look at what is going on there. So the optical power built inside the cavity keep increasing. And then at a certain point you go to, say, dark fringe in gradual way. So the more you go to dark fringe, the more energy is built in the two arms, because basically you are getting less and less power to the output, and you keep building it inside, just you leave it inside the interferometer. So you see, look at the power. The power is really increasing in an exponential way as long as we are approaching the final, say, dark fringe, and you see that's becoming brighter and brighter. So, and then, okay, states keep changing, and then in a few seconds we should be able to reach the final, you see. But this is really impressive in terms of, so this is what you, and remember that this is a parasitic effect. What you see now in there, we would like not to be there. These are just the fact. You see, so we would like these things not being seen. So let's go back to that. Anyway, so this is what's going on in control room. Now again, all the automation is linked to website where you describe what is the current status of your system. You are saying, okay, we are locking at this stage, and so on. So, and then you are also providing to the data acquisition. I was saying before, since we are linked to the data acquisition, we are providing channels that provide the status of your system. This is one state machine that describe you what's going on for what concern. This is used for generating the noise budget, for example. And yeah, just a little note on version control. So you are developing really a lot of code, and we need to keep track of it. And so what we have done is that as soon as you start one of those node server or you load your code, this is automatically put under version control. And you see, this is very important. Once you have reached a status in which the system is working, you don't want to forget about it or try to go there, because again, the main point of what we are doing is reaching a stable condition, and all what we are doing, or great part of what we are doing, is really embedded in the Python code we are developing. So this, we must keep track of it. And one of the other main use of Python is development of user interfaces. You see, they come out also quite nicely. And this is the interface for the operator in control room. This is where they work and they control the machine. So conclusion. So the scientific community is definitely waiting for us. We are rushing to be there because we want to be there. Joining with the latest development I just showed you, we have a chance to join LIGO in July, August, let's hope so. And Python has been definitely very useful. So it's really helped us. No, it's not. I'm not just saying because I am in a Python conference. This is what has been. We also, me and some colleagues push a lot to have Python into the loop, and we have been successful. So this has been helpful. So thanks a lot for your attention. Just last things, since, as I said, it's just been sensitivity curve just made a few days ago. So this is freshly baked. First final product of the machine. If the thing is, come on. So if you look at the past, now we are somehow like this. So the curve I showed before would be something like here and like this. So it's like to be back in 2006 or something like that. But we know already many sources of noise, and we have already detected them. So most probably in a few days or a few weeks, we can already reach this area or something like this. So things can be done. So we can make it.
We have time for one question.
Have you found some bottlenecks or issues using Python in some way?
Not really. So what is going on at the moment is the following. As I said, the control loop we are dealing with is a slow one. So this is 1 second loop. Inside this 1 second, you can really do many things. But for the advanced things we have in mind, like for example, start doing parameter optimization for the parameter of your control, maybe some kind of algorithmic would be useful. So maybe in some time we may start hitting limitation in terms of performances, and this is why I was talking with the PyPy guy around to start playing with it and see if we can make improving the. But so far there are no limitations. As I said, this is really slow control. But we would like, you see, the field of application is really keep increasing. So we are moving toward a bit the fast control. And also maybe, again, try to do massive data analysis for optimization of the parameter, of the control parameter of the detector. And this is why I may imagine that in a while we may start hitting so performance limitation, and PyPy may save us on this side.